Some railways should not be possible. They crossed the things that, for most of human history, simply stopped us. The deepest mountains, the open sea, ground that refuses to stay frozen, and the border between two nations. This is how engineers crossed them anyway. To run a train, you need ground that is flat, solid, and predictable. Nature almost never provides it. For centuries, a tall enough mountain, a wide enough strait, or soft enough ground was simply the end of the line. Then engineers stopped going around these obstacles and started going through them, boring tunnels kilometers beneath the surface, freezing the very earth in place, and driving machines straight through solid rock until they met beneath the sea. In this episode, we'll follow 4 of the most extreme railways ever built: a tunnel deep beneath the Swiss Alps, an undersea crossing off the coast of Japan, a line across the frozen roof of the world, and a passage beneath the English Channel. 4 impossible problems and 4 very different answers. Beneath the southern Swiss Alps, trains now race through solid rock at 200 kilometers an hour. The Gotthard Base tunnel runs 57 kilometers, from Erstfeld in the north to Bodio in the south, the longest and deepest railway tunnel ever built. But its real challenge wasn't length. It was the mountain pressing down from above. In places, more than 2,300 meters of rock sit overhead. That is the impossible problem the engineers had to answer. To understand the danger, picture a cross-section. 2 single-track tubes run side by side, with the whole mass of the St. Gotthard Massif bearing down. Under that much overburden, weak rock behaves strangely. It doesn't crack, it flows. Engineers call it squeezing rock. The stone slowly pushes inward, closing the bore like a fist. The answer was to line those sections in concrete immediately, before the rock could converge. The twin tubes also serve safety. Cross passages link them every 325 meters, so each tunnel becomes the other's escape route. And deep underground, rock temperatures climbed toward 46 degrees, so powerful ventilation and cooling held the working face livable. Boring 57 kilometers from 2 ends would have taken decades. So the engineers opened the mountain in the middle. Access tunnels and deep shafts at Amsteg, Cedron, and Fido reached down to the route, letting several boring teams attack different sections at once. Around 56% of the tunnel was ground out by giant boring machines. The rest was blasted by hand where the rock was too hard or too broken. Working in parallel, they cut years off the schedule, and in 2016, after roughly 17 years, the tunnel opened. Today, that engineering is invisible to the passenger. The train simply glides flat and straight beneath 2,000 meters of Alps, where mountain railways once clawed slowly over the passes above. An impossible mountain, answered with concrete, machines, and patience. But the Alps are solid ground. The next barrier engineers faced wasn't rock at all. It was the open sea and the cold water of a strait that had to be crossed from below. The Gotthard went straight through the heart of a mountain. This one does something stranger. It dives beneath the sea. Off the northern tip of Japan, the Tsugaru Strait separates the main island of Honshu from Hokkaido. Cross it on the surface, and you face brutal storms and treacherous water. So engineers asked an impossible question. What if the railway simply went under it? The answer is the Seiken Tunnel, 53.85 kilometers long, with more than 23 kilometers running beneath the seabed itself. When it opened in 1988, it was the longest undersea railway tunnel on Earth. To understand why this was so hard, look at the depths involved. At its lowest point, the track sits roughly 240 meters below sea level and about 100 meters below the seabed, with up to 140 meters of water pressing down from above. At that depth, the sea exerts crushing hydrostatic pressure, and any crack could mean catastrophic flooding. The seabed geology made it worse. Hard rock, hidden fault zones, and sudden inrushes of water that flooded the works during construction. So the engineers chose their path carefully, driving the tunnel deeper, through more stable, better quality rock, even where the water above was at its deepest. Their answer came in stages. Before the main bore, crews dug pilot and service tunnels, experimental sections to test methods and watch for water before committing. The finished tunnel was wrapped in thick linings, and continuous waterproofing to hold back the sea. And because this is earthquake country, they built in seismic-resistant detailing and 2 undersea emergency stations, with stairways reaching toward the surface for evacuation. A railway, running calm and dry, 100 meters under the floor of the ocean. From the deepest sea, our next impossible problem climbs to the opposite extreme, a frozen plateau nearly 5 kilometers above it. The last barrier was water, held back by steel and stone beneath the sea. This one is stranger. Here, on the roof of the world, the enemy is the ground itself. The Qinghai, Tibet Railway climbs the Tibetan Plateau toward Lhasa, cresting near 5,000 meters at Tangula, the highest railway on Earth. But altitude isn't the real problem. The real problem is what the track is built on: permafrost. Frozen Earth, locked solid for thousands of years. Build a heavy railway on it, and your heat begins to thaw the very ground holding you up. Solid in winter, soft in summer, the roadbed sinks, buckles, and tears the rails out of line. So engineers tried something counterintuitive. Instead of just insulating the ground, they actively pulled heat out of it, keeping it frozen on purpose. They call it positive cooling. Look at the roadbed. Beneath the track sits a thick layer of loose crushed rock. In winter, cold, dense air sinks into the gaps and convects downward, chilling the soil below, a one-way valve for cold. Then come the thermosiphons, sealed pipes driven into the embankment. Inside, a fluid boils with the ground's faint warmth, rises, sheds that heat to the frozen winter air, condenses, and sinks back down, pumping heat out with no power at all. Together they lift and hold the frozen layer right beneath the rails, season after season. Where the ground was warmest and richest in ice, they stopped touching it altogether, raising the line onto viaducts, so cold air flows freely beneath and the heat of the track never reaches the soil. Opened in 2006, it remains the longest railway ever laid across continuous permafrost. And its greatest test is still coming: a warming climate, slowly thawing the very foundation it stands on, which is why the cooling never stops. From frozen Earth at the roof of the world, we descend to one last barrier, a crossing not over land, but beneath the sea, joining 2 nations long divided by water. Our final project doesn't cross a mountain or a frozen plateau. It crosses a sea border. Beneath the Strait of Dover, the narrowest neck of the English Channel, runs the Channel Tunnel, linking Folkestone in England with Coquelles in France. At just over 50 kilometers, it isn't the longest rail tunnel ever built. But of that length, nearly 38 kilometers lie under the sea, the longest undersea stretch of any tunnel on Earth. Boring under open water carries one overriding fear: the water itself. A single fractured seam could flood the works. The answer lay in the rock. Engineers held the entire alignment inside a thin band of chalk marl, soft enough to cut quickly, strong enough to stand with little support, and almost watertight. Now notice the shape of it. This is not one tunnel, but 3. 2 single-track tubes carry the trains, and between them runs a smaller central service tunnel, stitched together by hundreds of cross passages and pressure relief ducts. That central bore is the heart of the safety design. Kept filled with clean, pressurized air, it stands ready as an escape corridor, so if fire ever breaks out, passengers cross into protected ground while smoke is held back. 11 tunnel boring machines, launched from both coasts, chased that single layer of rock until they met, far beneath the waves. Opened in 1994, the Channel Tunnel remains the only fixed link between Britain and the European mainland, proof that the hardest barrier to cross is sometimes not rock or ice, but the sea itself. Step back, and the scale speaks for itself. Line the great tunnels up side by side. The Gotthard Base Tunnel, 57 kilometers, the longest railway tunnel ever bored. The Seiken, just under 54. And the Channel Tunnel, 50.5, third by total length, yet first beneath the waves, with the longest undersea run of any tunnel on Earth. For projects, for impossible problems, a mountain that tries to squeeze its tunnel shut, a sea that wants to flood in from above, ground that turns to mud the moment it warms, and a border written in water. None of them was beaten by brute force alone. Each was solved by studying the enemy closely, the pressure of the rock, the weight of the water, the slow thaw of the ice, and then engineering a reply shaped exactly to it. That, in the end, is what engineering the impossible really means. Not overpowering nature, but understanding it well enough to find a way through. If journeys like this fascinate you, stay with us, because somewhere out there, the next impossible railway is already on the drawing board.